Welcome to Regulated Power Supplies, Part 9. So here is the evolution process of our power supply, and we've got variable voltage control now, 5 to 35 volts for this supply that we designed. Now, this is great. This supply is great as long as the output doesn't get shorted. So what I'm saying is basically we have a minimum RL. We can go as big as we want at a certain RL. But if we bring the resistance on the output down too low, we will this power supply will destroy itself. So this circuit is the solution. And we're going to see how this circuit prevents or protects the circuit from destroying itself when the output is shorted. So we call this fixed current limiting. So we're going to provide fixed current limiting where if somebody shorts the output or something happens with your load, it's not going to destroy itself. And part of that, we're going to use op-amp regulation. So you can see now we've switched out that one transistor for op-amp regulation. And you can see diodes D1, D2, and D3. They're actually going to be what's basically providing the trigger for the current limiting. All right, so we've got our 741 that we're going to use to help provide the current limiting. You can see the diodes D1 through D3. They're specifically helping with our fixed current limiting. But we're going to use a 741 and we need to know the voltage on pin 7. What is the maximum voltage we could do for the supply voltage when we're grounded? Now, the data sheet says that we've got a nominal of plus and minus 15 volts, meaning that the plus pin can be 15 and the minus pin can be minus 15. But the differential, all this op-amp cares about is the difference between those two. So that means I can put ground on pin 4 and 30 volts on pin 7 and it'll operate fine all day long. So we're going to put 30 volts there, designed for 30 volts pin 7. Now we know that the LM741 is not a rail-to-rail op-amp, meaning that it cannot go all the way on the output. Pin 6 cannot go all the way to its two extremes, V plus and V minus, pin 7 or 30 volts and ground in our case. And the number that I usually use for trying to calculate what the max out and min out would be for an op-amp 741, because there's some internal voltage that's needed there, I usually use 1.4 volts, like 2 diode drops or 2 VBE drops internal to the device. So if I start out with 30 volts, that means the max I'm going to be able to get out on pin 6 is 28.6. And if I try to rail all the way down to the negative side, the max this thing will be able to, the minimum it will be able to do is 1.4 out, 1.4 volts out. So if I've got 28.6 volts, you know, what can I fit? What will my new? I can already see that that's less than my 35 volts. But what can I actually get out of this power supply, out all the way out to the output? And if I've got 28.6 volts on that pin 6, I need 0.7 volts for VBE Q2, 0.7 volts for VBE Q3, or sorry, Q1, and also whatever VR5 is. And you can see the 3 diodes are in parallel with the 2 VBEs and the R5. So now you know as R5 voltage comes up, the max it's ever going to come up to is 0.7 volts. So that gives me 2.1 there. Subtract that from the 28.6. That gives me a maximum V out for this circuit with a 741 of 26.5 volts. So if you wanted more voltage, you'd probably need to go get a different op-amp that can handle. And I always design for nominal. I know it says plus and minus 22 volts there for a 741A, plus or minus 18 for the C. I think you're just kind of pushing things if you're running at the extreme, and the recommended operation nominal is 15. So just for me, if I wanted to go higher, I'd just go find a different op amp that was happy running at that higher voltage. And so knowing all this, we're now going to choose a new max out for our power supply of 25 volts because we know we can get to that. And so our new voltage that we're going to design for this power supply is going to be 5 to 25 volts. Okay, so now let's take a look at R3 and R4. That's going to be very, very similar the way we calculated it in the previous circuit. The first thing we need to know is what I'm going to call the control voltage, which is right there on pin 2 of RV1. And if we follow that wire back, we see that it's attached to the negative input of the op amp, pin 2 of the op amp. So if we remember anything from op amps last semester, we know that with feedback that the op amp is going to do whatever it can to keep the two inputs equal. And I know it's maybe a little bit hard to see the feedback path here, but the feedback path is through that pin 2, through the resistor network, the variable voltage resistor network, back through the Darlington pair and to the output of the op amp. So there is feedback path here. So we now know if the Zener Z1 is a 3-volt Zener, and we've got 3 volts on pin 3 of the op amp, that would mean that we have 3 volts on pin 2 of the op amp, meaning that we have 3 volts on pin 2 of the variable resistor controlling our variable voltage range. And so now I just wrote 2 loop equations just like we did in the previous video, and if you need to see the math worked out in detail, I provided some of the math here and the final answers. Go back to that other video and because that one is in detail on how to work the math. And so I ended up with an R4 of 214.286 ohms and an R3 of 607.143 ohms with a 4.5 and 25.5 volt min and max. And that 0.5 volts, it's not because I want to make sure I get 5 to 25 volts. I'm giving myself a little bit of padding here. So when I finally do throw standard values in, you know, and tolerance, consider tolerance is when we build this thing, that I will actually be able to achieve my actual goal. And you can see when I throw the standard values back in, I've got the standard values I looked up in Mauser, 215 and 612. When we put those back into the equations, we get a 4.511 volts all the way to 25.49 volts. All right, so we talked about the op amp. We talked a little bit about the fixed current limiting, but we really just redesigned and set everything up for standard values for R3 and R4. And we're going to continue building and designing the rest of this circuit in the next video.